Okay, ladies and gentlemen, today we are going to talk about reversible and irreversible processes as well as Carnot efficiencies. And the first thing, reversible and irreversible processes is what we're dealing with. So we talked about cycles in class on Wednesday, but now we're going to talk about processes. And reversible and irreversible is going to be talking about that idea of perfection. A reversible process is perfect. It's the situation where we're talking about that sand in our hands or the glitter in our hands, and we can move from point to point and we don't lose any of it. It doesn't go out and put onto our surroundings. Now, in reality, we're going to be able to have some reversible processes, but not any reversible cycle. Okay, so that I have to understand the difference between a process versus a cycle. Okay, processes we can have some can be reversible, which means perfect. And we'll talk about those here in a second. So let's define what a reversible process is. Reversible means it can go one way and then back again without leaving any trace on the surroundings. Okay, now irreversible processes is easy. It's just a real process. These have heat loss and friction, and all those things that we can we know are real that happen to us. Okay, so if an irreversible process is real, then why consider reversible processes? Well, it's very similar to why in dynamics class we deal with frictionless surfaces, or we deal with frictionless pulleys or all that kind of stuff. But we do it in our everyday life. I mean, we think about what is the best that we possibly can reach, and that's the reversible. And that's what our goal is. Okay, you do this in dating. You have a list of things that you want, or if some of you are out there married, the list of you that you want, what you want in a mate and what you want in a partner. And you look for those things. And you know what? You're not going to be able to check every single one of those boxes. You're going to have to decide how many of those boxes need to be checked for me to be happy, for me to be content, for me to be able to stand, to be able to find somebody that I can live with. And you know, if you look for every single one of those check boxes, you might be searching for a long time, but you might say, you know what, there are some certain check boxes that have to have checked. And so, you know, we look for that. We look for that. And then we say, okay, reality is I can't find a 42-year-old bald thermodynamics expert who is wearing his hat backwards today because it's reversible process day. You know, you can't find that just anywhere. That's a special situation. So you have to settle for reality. That you have a bald 42-year-old man who makes stupid jokes and I don't know, has braces at 72 years old, at 42 years old. You know, those are the kind of things that you see if you can't work with. Okay, so as engineers, we model reversible. Okay, the best we can obtain. We see how close we can get. Now, the farther away that we get from reversible processes, the more entropy we produce. So our goal is to produce a little amount of entropy as possible. Okay, and so we want to limit those irreversibilities, those things that make the cycle real. Okay, now there is something called an internally reversible process, and it's completely valid in everyday life. So let's talk about it. Let's go for it, internally reversible. Okay, internally reversible process. Okay, so let's go here and let's put into this internal system, this internally reversible. So we have a system internal, like a closed system here. Let's put water here. Water inside of this piston cylinder, and let's add some heat to this water. Okay, so add some heat to this water, just Q here. And what's going to happen to that is we keep adding more and more and more heat. Well, this water's going to expand. It's going to expand probably bigger than this. But here's going to be my control volume. And we're going to say that this is going to go and look, it's going to turn into steam. And then if we remove heat from the steam, what's going to happen is we're going to go right back to where we came from, and we're going to have water, liquid water. So if our perspective is only internal to this piston cylinder, we see that we go from water to steam to back to water. Process, we add heat and we remove heat and we go back to water. This is an internally reversible process. If our perspective was only that, if we could see only around us, it looks exactly like it is reversible. And internal to that piston cylinder, it is irreversible. However, if we were to expand our point of view beyond the piston cylinder, maybe just into the piston walls, what actually happens is some of that heat that is coming in from the surroundings goes into the piston walls, and as it goes around that piston, is dissipated around. Now, some of it makes it into the water and heats up to steam, and that's all the water cares about. But not all of it gets there. And maybe the source of heat for that water is a flame, okay? That flame, not all the heat is going directly into that water. Some of that heat is going out into the environment around it. So if we make the control volume bigger, we will see that it's not really a reversible process, but it is internally reversible. Okay, so that's what we need to think about. Internally it looks reversible. Make it bigger? Not quite. Not quite. Okay, so that's what we'll end here talking about reversible and irreversible processes.